Hello, everybody, and welcome to the webinar. It will be beginning shortly. We're going to take just a minute to let everybody get in the room, and then I will introduce our webinar and we'll get started. One more minute. All right, I'll go ahead and get started. Welcome, everybody, to Rules for Tools, Characteristics of Effective Ergonomic Assessment Tools, presented in partnership with the Deep South Center for Occupational Health and Safety and the Center for Occupational Safety, Ergonomic, and Injury Prevention at Auburn University. Just a little bit of housekeeping items first. As a reminder, you will all be muted. If you have a question, please enter it into the Q&A box, not the chat, at the bottom of your Zoom screen. We will ask all the questions in there to the panelists at the very end of their presentation. You will get a copy of the slides as resources and a recording in your email tomorrow with the evaluation that will lead you toward your certificate worth 1 continuing education contact hour. At this time, I would like to present our speakers, and we'll go ahead and start off with Rich Sesek from Auburn University.
Thanks a lot. I'm here with my brother Bob. We've got AJ and Murray, and I'll do just a kind of a quick brief introduction for us. I'm going to apologize in advance and turn my camera off due to bandwidth. I'm actually in Arizona right now, and I wanted to save a little bit of bandwidth. All right, so I teach at Auburn University. I do research in ergonomics and safety. AJ was a PhD graduate last year. He's now working at Tesla. My brother Bob, full disclosure, nepotism, whatever, he's actually a student with another professor in our department, and Murray is working with me on his dissertation. And information on, if you want to reach out on LinkedIn, is available in the slides. So our we'll start with what is an ergonomic assessment tool, and the answer is that an ergonomic assessment tool could be as simple as a tape measure, but we tend to make things more complicated maybe than they need to be. So what we want to talk about today, though, is what is the goal of ergonomic assessment tools, and this idea that really what we're trying to do is objectively determine work-related musculoskeletal disorder risk that's associated with both the tasks and the jobs that are built from those tasks. There's a lot of assumptions that we make when developing ergonomic assessment tools and when employing ergonomic assessment tools. And some of them are that the assessments are based on something representative of the actual exposure. And we'll talk about that in greater detail as we go through the presentation. The likelihood and severity of the outcome is related to the tool output. In other words, a higher score or attribute on the tool output would result in a higher level of risk. We also further assume that the data can be used in a meaningful way to prioritize tasks and jobs for improvement. So the objectives we have for this webinar are to present what we think are the ideal characteristics that an ergonomic assessment or surveillance tool should have. We want to familiarize attendees with some of the limitations of ergonomic assessment, and we want to suggest ways that you might be able to best apply and interpret the tools. Throughout, we'll try to show little lessons and caveats regarding these tools, and we'll recommend some areas of research focus for the future. So some key points up front. Damage and the buildup of physiological fatigue from physical stressors are nonlinear. And so is the probability of an injury resulting from that damage. And what we mean by that, an example I like to give is if I ask somebody to lift 500 pounds, once is too much. They're going to hurt themselves. But they could probably lift 50 pounds 10 times, or 10 pounds 50 times, or 1 pound 500 times. If we assume a linear addition of risk, then those all would be the same. And intuitively, we know that they are not the same. Things like fatigue failure, MAE and RCRA, they can help explain this risk in terms of the nonlinearity associated with these forces. They're straightforward ergo assessments that are based on these principles. We wanted to just underscore, we all know this, but the workforce is changing. It's increasingly obese and aging. In addition, we have potential impacts due to COVID that we don't even know what they're going to be, with people losing some degree of their lung function or even cognitive ability moving forward. We're going to mention that job rotation may actually increase overall risk in some cases because we're rotating more people through a difficult task. And we're going to just implore you all to fix the worst first. Our experience with ergonomics is that the worst task will disproportionately be represented as damage and therefore risk. So a little background, epidemiology is used to evaluate and validate ergonomic tools. And I want to give a little background on some of these tools and some of the way we use these statistics. So we've all seen something like this if we've been in ergonomics for a while, this notion of a kind of a 2x2 outcome matrix. And this is, in fact, one of those little lessons we want you to kind of focus in on. When we evaluate tools, we often look at the 2x2 or the dichotomous outcome. We look at the, it's a binary. It's the tool score is above this, it's hazardous, it's below this, it's not. In this case, we've got our true positives, that the tool got it right. It said it's hazardous, and there was, in fact, an outcome. It could get it wrong, false positive. It says it's a problem, it's not. It can get it right. It can say it's negative, it's safe, and there's no injury. And of course, we could have a false negative. And we're going to go through each of these and hopefully give the practitioner a little bit more insight into what researchers do when they're trying to evaluate some of these tools. So this is more for your reference. We'll go through this fairly quickly, but I think this is useful. All my PhD students, we go through this. I want them to understand this. So we take that same green is correct and red is incorrect, our little 2x2, to look at different measures. One of those sensitivity is simply the percentage of the true positives, of the actual positives that we got. So it's the true positives plus the ones we missed, the false negatives. It's what we use in research often is we look for sensitivity and specificity. We say, we've got this percentage of the actual cases correct. Whereas specificity is the percentage of the controls or the unhurt people that we correctly identified. And just as an example, specificity and sensitivity can be artificially inflated in certain ways. For example, if I said everybody on this webinar is a convicted felon, well, I've identified all the convicted felons, but I've also got a lot of false positives. Now, hopefully there's not any convicted felons, but likewise, if I said, nobody's a convicted felon, well, I'd have 100% specificity in that I identified all the people that aren't, but I might have a false negative in that there might be a felon among us, right? So these are the two measures, sensitivity and specificity, that often get used when we're evaluating tools. I think that positive predictive value and negative predictive value are better. Now, what are those? Those are really, it's a conditional probability, really. It's the probability, given that I said it's a problem, that it is a problem. So it's if I predict someone's going to be hurt, it's just the percentage chance that they actually are. Similarly, we have negative predictive value, which does the same thing. Now, if we look at positive predictive value and we graph it, this is actually for the cumulative lifting index. This is from an automotive study, 1,100 workers performing over 700 jobs. This is the positive predictive values that we saw for various cumulative lifting index scores. It's the NIOSH revised lifting equation. And what you see here is as the score goes up, the probability that they hurt goes up with it. And if we look, our normal cut point here is 3. We say it's over 3, it's probably hazardous. Notice about half of those jobs, and then in the outcome in this case was reported a first-time office visit to medical. So someone went to medical because of a problem. If we look up here, we see that once the score was 4 or 5, every single person in this study that we did had reported to medical for some symptom related to low back pain. So what we're saying with this is, we have on the next slide, and that is that the cumulative lifting index of 3.1 and 2.9, if 3.1, if 3 is our cut point, how much more hazardous is it? Well, they're really very similar. If we look at our graph, we can see that if it's about 50% at 3, it's going to be slightly over 50 and slightly under 50 if we're close to that. And, you know, if we all know that if we've done an Irish lifting equation, you're holding a tape measure next to someone's hip, you could be off by an inch, and that could be all the difference. In a similar vein, a strain index score of 7 or more is considered hazardous. Would that mean that scores of 9 and 36 are equally hazardous? Of course not. We would assume that the higher the score, the more likely the outcome is, the negative health outcome. So the risk or probability of a WMSD should increase with increasing scores if the tool is valid. That's a rule that we would, if you're using a valid tool, this should be true. Therefore, when you do an assessment in your workplace, you should be paying much more attention when those scores get very high. So high strain scores, high CLI scores, et cetera. So negative predictive value is just basically the same thing as positive predictive value conceptually, except that we are looking, this is the identifying which jobs are probably safe. When I did the large automotive study, this was something that was very important to them. They wanted to know, hey, can we not look at this job and feel pretty good about that? In other words, they wanted to, if you take a traffic light analogy, they wanted to know which jobs were green, which jobs were yellow, and which jobs were red. Now, odds ratio is something you'll see in a lot of papers. And this is one way that we identify whether a tool seems to be working or not. And I'm going to tell you that what all it is looking at everybody above a certain point versus below a certain point. So the cut point, let's say it's 3.0 again, we take all the ones we got right, the true positives times the true negatives, divided by the ones we got wrong, false positives and false negatives, and that gives us a likelihood ratio of that person being hurt if their score is above 3 versus below 3, for example. So this is often how tools are used. I had an important lesson I learned as a graduate student, and that was that the odds ratio actually changes a bit. And if we look here, it's fairly consistent between 2 and 4. So a person with a score above 1 versus a person with a score below 1 is roughly twice as likely to have an injury, for example. As the index goes up, that ratio goes up. And here's our ratio, our magic cut point that NIOSH had suggested of 3.0, that's hazardous for most people. The odds ratio is 6, meaning if your score is above 3 versus below 3, you're 6 times as likely to be hurt. Now, I remember I was working on some research as a grad student myself, and I was looking at the literature, and Dr. Maris at Ohio State was, the Ohio State was calculating, he was getting higher odds ratios than me. And I was playing around with the idea of different cut points. I said, what if I compared 3, those over 3 to those below 1? And then I got the same odds ratio that he got. And I looked and I read his paper for the 3rd time and actually saw that he did that. He compared above 3 to less than 1. The lesson here is that any single point, we're looking at people who may be close to that decision point. The higher the decision point, the more likely they are to be hurt. This point here is a 0 odds ratio only because everybody over a certain point was actually injured. So that's why it came out as 0. There were no true negatives that were missed. So when we look at research, we look at a case control kind of concept, the case being the person who's asymptomatic, the case being the person who is actually hurt, and the control being the person who's unhurt. If our tool works, the difference between between the scores, so see a natural kind of a concept is, let's make a decision point. Now, intuitively, people want to aim here and say, hey, this is where the two curves intersect. It must mean something. But we'll talk about how you might adjust that, moving forward for what's considered hazardous and not hazardous. So in this case, if I move the decision here, what happens? Most of the people are going to be hurt. This tail, we know is going to extend, but we have a very high positive predictive value and a high specificity, meaning we've identified all the controls, they're over here, but we also have a lower sensitivity. We missed almost half of our people here, and a low negative predictive value because the people below include all of these people as well. Similarly, we can go the other direction. And unfortunately, a lot of tools are like this. They cry wolf. If every job is hard, then no job is hard. And if they classify everything as hazardous, that means the ones below, they probably really are negative. And we have good sensitivity, but we're wasting resources potentially in doing an investigation of jobs that are not going to hurt people. Now, if we look at this, all I've done is separate the distributions a bit more. And you can see here that this would be a pretty good tool. There's very little overlap. Whereas this would be a poor tool because there's very poor differentiation between the two. And this would be a tool that's like flipping a coin. It doesn't really give you any information at all. So if we look at a case control, something like this, we've got two distributions. Now I've gamed this a little bit. I played with this to make this about 25% of the area under each of these curves. And in which case our performance will be, all the metrics will be 0.75. We have a prevalence of 50%. In this case, we have an odds ratio of 9. What that means is anybody above this point is 9 times as likely as people below this point to be hurt. If we look at sensitivity, it's simply how many of them that we got. These are the cases that we got right, 75%. Specificity, the percentage of the cases that we got right, or sorry, the controls that we got right, in this case, 75%. It's a little more complicated, but I'll walk through this, you can see it, but positive, negative predictive value. For positive predictive value, I got 3/4 of my cases identified, but I also missed 1/4 and have an extra quarter of the ones from the controls. So again, it's a 0.75. So it's not so bad, 75% likely. And the same thing is true when I do negative predictive value. I've identified 3/4 of my controls properly. I missed 1/4 of them, and I have 1/4 of my cases in there. But this is the reality, and here's the lesson I want you to kind of focus on, and that is that the prevalence of a disorder is often very small. In fact, if we're doing our job right, hopefully it's very small. We don't want to have a prevalence over, do we want 50% of our people in our factory to have carpal tunnel? I don't think so. This is usually a tiny percentage. So what do? We've got decisions to make. And this is where sliding this bar, our cut point, if we have a single one, we may move it to the left in order to make sure we've identified all of the people who might have the problem. And then we can investigate further to make sure that we're controlling their jobs adequately. This really illustrates how prevalence makes a difference. So I have the same data in here. I just multiplied. These are factors of 10 away from the 50% prevalence. It's the data I showed you before, odds ratio 9. Odds ratio stays the same. My sensitivity and specificity stay the same, but my other values suffer. And in this case, positive predictive value. An indication of this, and there's a little counterintuitive thing, but if I have a test that is 99% accurate, let's say it's for hepatitis or AIDS in the blood supply, it's 99% accurate. If you test positive on that test, what's the probability that you have that hepatitis or whatever? And the answer is, it's not 99%. It's much less than that because the prevalence is so small. And what we do, if we're clever, we set our test in such a way that nobody that has AIDS, hepatitis, whatever, their blood gets into the blood supply. So what we do, we test those people again, and the likelihood that they test positive, false positive again, is pretty slim. And that's what happens with, we can do an analogous thing with ergonomics. We want to make sure that we're really looking at those. We want to make sure we capture all the cases. So again, the odds ratio is the same in all these cases. The prevalence is different. The sensitivity and specificity, which is often how tools are evaluated, is the same regardless. But the value I think is important is this positive predictive value. And we see that it's not the same in all those cases. The other issue with developing tools is what is the outcome definition and how does that play a role? So for example, what constitutes an injury? Is it symptoms? Is it a report to medical? Is it a specific diagnosis? Is it lost time? Is it workers' comp? Is it the severity of the injury? And I would submit to you that if you play a recreational sport in your church league basketball or you play softball, if you're injured and you can't play, that injury is not your leg doesn't snap off. It may be just enough, some threshold that you don't play. And when you come back to play again, it may not be at 100%. And that's one of the issues we have with ergonomics is how do we define who's injured and who's not? What symptoms matter? How much discomfort is normally associated with the job, for example? So we talked about some of the other limitations and this idea of a representative task. Now I want to show this job and I'm going to ask questions. I'll have it go slow and then speed up. So is this the job? Is this representative of what this guy does? He's reaching pretty far in front of himself. Pulling down fairly forcefully. Some cases with two hands. Now I speed up a little bit. Go to another part and we say, is this the job? Now imagine certain tools that are snapshots in time. Do I do, for example, a ruler on that or on this or this or this? So you could see that even the video itself may not be representative of the job. So there's some variation here. Do I have a representative sample? Is this a good assessment of what this person does? And you can see all the different things that this person does. At one point, they're placing tiny objects on, lots of dexterity, fingers putting things in place. For the most part, the left arm was busier than the right arm, but depending on what I look at, I might not see that. So what does an ideal tool look like? Ideal tool has to be accurate, obviously, predicting these health outcomes. Should be reliable and repeatable, getting the same results each time. In fact, if it doesn't have reliability and repeatability, it's going to be very difficult for it to perform at all. It should be quick and simple. The example I like to give is if I have 2,000 people in my facility and I do in my ergonomic analysis takes 1 hour, that's 2,000 hours of time. That's an entire person year of effort just to get the ergonomic assessments done. And those jobs may change by the time I'm done. Whereas if I have a quick screen, I might have 2 levels of a tool where I can do it in 5 minutes. And then that 5 minutes informs me whether I should dig deeper. That might be another approach. And we'll talk about some rules for tools and rules for applying those tools. So the application interpretation should be consistent and clear. What does a score mean? How do I interpret it? It should allow for multitask and complex jobs. Many tools don't. Murray will talk more about that. It should facilitate prioritization of tasks within jobs, as well as identify which jobs are safe and risky, and which contribute most to the risk. What element of the job is contributing the most to the risk that person is seeing? The results should be invariant. I should be able to analyze the job in any kind of grouping or order. It shouldn't change. It should be consistent across a variety of workplaces, and it should account for differences in worker capabilities. And I mentioned this already, having a quick and a deep diversion. Notice I said ideal. I don't think there are any tools right now that do all of these things. Certainly not when you throw the word quick and simple in there. So just as a kind of a quick, and this is just our opinion, you may not 100% agree, but this is a breakdown of certain tools that are commonly used. And we could see here that many are not designed for multitask assessment. You notice on Nash-Lifting equation, I gave both a check and an X because if it's more than a few tasks, it becomes very difficult to do without some sort of software to do it. Also, the area where all the tools pretty much are hurting is in accounting for worker differences and having a quick or deep diversion. And in my world, the future tools, the ideal future tool should address all of these strongly. All right, so this is where we need the most effort, I think, in research. So as far as having rules to dictate how these tools are done, The tool input should be as objective as practicable. They should incorporate all of the significant exposures. Little minor things can be left off, but if it's significant, it needs to be included. Should account for exposure interactions, the force, posture, repetition interaction that may be taking place. Should be, again, repeatable. Without that, that's a necessary but not sufficient condition for actually having a good tool. You should not add a task and somehow have less risk, or remove a task and avoid, and it should not increase risk when you remove a task. So again, having adequate resolution to compare our tasks and jobs. As far as the rules for applying for the user themselves, the ergonomists themselves, the first is an acknowledgement that all tools are limited. Professional judgment may be necessary to adjust the risk up or down. Someone might have a disability or prior injury, for example. Tool must be appropriate for the task. Using the NIOSH lifting equation for lifting, not a hand-intensive task, for example. Tool scores should correspond to risk. High and low scores should represent very different risks, not simply above or below a cut point. Again, to underscore that, decisions should not be based on discrete cut points, but really having an understanding of the continuous measure of risk, understanding that risks are nonlinear. One 100-pound lift is not the equivalent of 4 25-pound lifts. And again, underscoring rotation may not reduce risk, but may actually increase it.
For the population.
For a given population. So for the overall population, I should say. Obviously, if you have a very bad job and you rotate to other jobs, your personal job does get better. I'm going to turn it over to Murray, who's going to talk a little bit more about some of these nonlinear relationships.
Hey, some of my interest kind of spawned, I saw a presentation, Dr. Sesek's about 7 years ago, and there were two bullet points. One is that the average tends to underestimate the rating, and when you use the worst case, it tends to overrate it. So I've been interested in seeing how I could quantify that. And this is particularly important when you have a nonlinear relationship between the model input variable and the output metric, as most of the times we do. But here's looking at the revised strain index. You can see the applied force, the percentage of your MVC or maximum strength. And then you look at on the y-axis, the multiplier or your the resultant score there. But if we forward to the next slide, and notice how it's nonlinear. So it's flatter on the left-hand side of the X, and it gets steeper as you go, as your X increases. But if we look at if we look at the X-axis, if we look at the red, a 20% difference, go from 20% to 40% of your maximum. Notice it looks to be about a 2.5 point difference in your multiplier. You go from about 2.5 to 5. Whereas if we look toward the right side of the X-axis, if we go from 70% of your maximum to 90%, say if my maximum was 100 pounds, if I went from 70 pounds to 90 pounds, that would be moving 20%. But notice if we go 20%, now we have about an 18-point jump. So the difference, you can see that if you're on the left-hand side of the curve, it's not near as steep, and it doesn't impact your resultant metric as much as the ones on the right. And generally what that tells us, if we're looking at, say, with the fatigue, or we're looking at fatigue failure, tissue damage, it's the higher forces that tend to, or the more extreme force values tend to have a more of an impact than lower values do. Now, if we go to the next slide, this is if we look at a multitask profile. I've always been frustrated. Many of the single task models, you can only put in one value for force, for frequency. So you wind up using the average. And you see here we have a 10-pound force for 2 seconds, 25-pound force for a half a second, and a 12-pound for 1 second. And our average is 15.7. We could do a little bit better. We could do a time-weighted average. And then the next one, or we can use a worst case. And typically, when a model is published in the instructions, it says either use the average, or if you want to be, exercise be more cautious, you could use the worst case, be more conservative there. Now here's an example. If we have 4 big forces and 4 little forces, this is one kind of I can sort of put together. We help us see this. So say if we had 4 big forces and 4 little forces, and then the next one, okay, this is if we use the average. This is what we see on the left. We have 8 forces of 21.2 pounds if we averaged all of those. Or if we use the worst case, we have 8 forces of 36.8 pounds. So that's what your model sees. Your model doesn't see the variation. It sees the average. The next one. Okay. This sort of sums it up. I used the RCRA, the recommended cumulative recovery allowance model that Dr. Jim Potvin, I saw he was an attendee. Even I published in 2016. We collaborated on this, but this is using the RCA model. It's a multitask model, so it can look at forces of different magnitude, and you get one resultant metric. But the problem is I was interested in figuring out the error due to using single task models, and you can't make a single task model. Naturally, you can't make it multitask, but one thing you can do with a multitask model like the RCRA is you can run it as a single task model. Instead of looking at each force independently, you simply do an average and you enter the average value. So you can see if we assume that the 0% error, say if the model was perfect, which it's not, but say if our RCRA ratio was 5.0, and that's a ratio of the calculated recovery time to the actual recovery time. If our true rating was 5.0 when we ran it as multitask, say that was 0% error, then we could run that model as a single task model. We could average those forces. And what that tends to do, it tends to undervalue it tends to give you a score that's too low. Or if we use a worst case, and notice our ratio was 5.0. When we ran it as a single task model as an average force input, it said it was 0.7. So it said it was okay. It was less than 1, but it was 86% too low. And then if we ran it as worst case, it was 100% too high. And you don't really need to understand the RCRA or RT is recovery time. Not necessarily that you understand what all those are, but generally it shows kind of the trend that a single task model, if we use the average input, is going to undervalue the exposure. Or if we use the worst case, it's going to say that it's higher than it really is. And interestingly, a lot of the calculations I performed, it's less inaccurate to use the worst case. And I remember I was someone I was communicating with from Ford was telling me about they were using the worst. Sometimes a lot of times they use the worst case, and I thought, well, that doesn't make any sense. But then when I run these numbers, I see it does. It's less inaccurate than using the average a lot of times. Okay, the next slide. Now this shows an example of nonsensical results. Say we have 2 big forces, 36.8 pounds, and then we have 2 little forces. Well, what happens if we remove one of those little forces? If we go to the next slide. Well, I'm sorry, go to the previous, go back one. Okay, if we took an average there, our average force is 21.2 pounds. Okay, now say we had a lean team working on a project. They eliminated the need for one of those little forces. We removed it. It makes the job slightly easier. Okay, now our average force is, we remove one of those forces, our average is 26.4 pounds. Well, what that does, we increase the average force by about 25%. And even though you did eliminate that repetition or that time that you're applying the force, almost inevitably what happens is it increases your metric, because if you're due to the steep nature of the nonlinear relationship, if you average something and it pulls your value down to that curve where it's less steep, it's not going to be as impactful. So what it does, it kind of mutes your higher forces or the impact of those high forces. This is a risk assessment timeline for the tools. I was sort of interested. I used to say that these tools, a lot of these tools we use are 10 or 15 years old. And now I realize I'm getting older and they're actually 30, 40 years old. some of these tools. And so, but this is, we can see, it's interesting, there are periods of time where it was very prolific. There were several tools published, like look at 1995. But what's interesting is to look at the multitask and single task models, and more than the newer tools are multitask in red. So the Auburn University fatigue failure tools and the RCRA or multitask tools, and even though revised strain index and what was the other one? But anyway, so some of the tools can be made multitask, but that's more through statistical weighting and things of that nature. But it's interesting to see more than the newer tools are multitask. Limitations of single task models. Many of these tools are 20 to 40 years old, and really it was designed for the pen and paper era. They represent static moments in time. One of the things I'm interested in is things like what happens if we change our make model mix, or if we change our rotation plan, being able to somehow assess that and be more dynamic and fluid and predict what's going to happen, rather than if we choose that static moment in time. That's kind of where we are. Dr. Sesek, do you want to jump in here?
Yeah, sure. These are there are a lot of the background for the tool, the motivation for the tool. It lacks a foundational model, and the thing about using recovery allowance and maximum acceptable expenditures and fatigue failure is that it accounts for a lot of that nonlinearity in there, and it creates a natural way for people to aggregate across tasks, which kind of goes along with our rules for what ideal tools might look like. And I think Murray, you had this is from your experience, some of the things that you had seen where these tools allow you to hone in on what the solutions are. If you want to comment on this for a moment, and then I'll take back over.
Yeah. So some of the projects where I've applied the multitask models, what's really neat is you can see the contribution of, with the single task models, you get a rating for the entire job or the task. But with the multitask model, you can see the contribution of each step. So in the upper left-hand part of the slide, you can see if we have 5 steps, you can see that step number 2 has the lion's share of the contribution to the metric. So we know we need to fix step 2. It wouldn't help us that much to make an improvement to step 3. And also you can sort of get creative. I've seen one project, I think there were 19 different locations. They were shelf locations. So you can focus on locations and say if you were placing items, say we were looking at the shoulder. And so some of the higher shelf locations might be more problematic. And 2, sometimes we can look at by item weight. You can see that some of the heavier weights, say if we had items of varying weight, we could do calculations, could do a weight distribution. And here we see items that are more than 10 pounds have the, much more significant contribution to the metric than we did for items less than 5 pounds. So we see if we focused on the heavier items and some of the more challenging locations. And one project in particular, I remember it was a complex job. It's like, well, how in the world am I going to sort out this? But in the end, it was very simple what needed to be done. They needed to stop handling the heavier items in the higher shelf locations. And but anyway, so a lot of times it can provide clarity of what needs to be fixed, because you can see the contribution of each metric, and you can sort of, like I was showing, kind of sort it out or divvy it out by other categories like weight and location.
Yeah, so these multitask tools will allow you and focus you on the worst so you can fix the worst first, which is, again, one of our little mantras here, we think is very important. So, why are we all here? How much can a person, lift, a specific person, by the way, push, pull, carry, exert, and do so safely? That's what we're really after. We have the other thing, the elephant in the room, is that we have physiological limits on our capabilities. We have differences in physical condition among workers. And even within workers, people go in and out of being in their best shape. For example, aerobic capacity, muscular strength varies among people, but also even within people. whether we're accustomed or unaccustomed to work, the concept of work hardening. We are an increasingly aging and obese workforce. And one of the best predictors of low back pain is previous low back pain. The gift that keeps on giving is back pain. So injury and illness status can also affect these things. The determination of what's safe, to some extent, at least for now, is going to include some level of professional judgment to include some of those other factors that may be missed by tools. There's no perfect tool. Being aware that there are certain critical thresholds of physiology and biomechanics and psychophysics that you exceed those, you're going to be in trouble. Basing things on epidemiological data, actual output data is important, and some combination of these can help us determine what's safe, with the idea that nothing is 100% safe. There's always risk. When you look at these tools, you say, oh, it's a score above this. Think of each one of those as a probability distribution rather than as the person's definitely hurt or unhurt. So with that, I just wanted to share a few things ongoing in future work that our center, the Deep South Center, has been working on, and things that we see as the future. So a peek behind the curtain here, we are working on deep dive tools. We're looking for model enhancements to include important variables that do not exist in the current fatigue failure tools, for example. We want to increase usability. I think our website could be made easier to use. We need further validation, including prospective studies. Some of the work that I'm doing, I know my brother's interested in as well, is a personalization. And then the idea of healing and strengthening and even improvement to somebody who may have, we go to the gym to get stronger, right? So if we increase our strength, we will be less likely we'll be working at a smaller percentage of our maximum at work. So these are things that we are currently working on. We've also done some work with using MRI to obtain better estimates of biologically relevant biomechanical factors that we can input into our models using regression. So I could estimate these from your height, weight, age, gender, easily obtained demographic variables. So we're looking at getting better estimates, for example, of back muscle lever arms. We're looking at the effects of exercise. We've had a couple of studies in this area looking at hypertrophy and also core strength among and balance among older women. We're looking at spinal health and trying to come up with objective measures that could be used to assess the damage that a spine may have undergone. So, another thing is some active fatigue failure concepts that we're exploring right now. In addition to cyclic loading, we're looking at creep loading of the flexor digitorum and profundus superficialis tendons in the wrist, and including residual strength and the impact of stress range on fatigue life. A PhD student is currently working on this. Nathan Poole has been testing samples actively for quite some time now. Here's links. They'll be in the notes that you will be provided. You can go check out the tools. I think Jessica is going to send you those. And I always like to end with a call to action. What is it that we think we need in this area? And I would say we need industry, academia, consulting, practitioners, all to partner in this development, testing, validation, and improvement of these tools. And this is going to be done in one way to do that is access to plants with a variety of jobs, the pooling of data from multiple locations, and epi-validation studies that include, in a lot of cases, the pooling of these data. Feedback on use and usefulness from a broad range of ergo tool users and stakeholders. I would argue that the greatest unused tool in the world is not only useless, but negative because it's a waste of the resources it took to develop that tool. And finally, I appreciate the continued ERC funding. I love when the ERCs get together like this workshop in order to share what we're all working on. And the current group of grad students I know that we have at the Deep South Center, I wouldn't trade them for anybody. So I think we're doing a great job. I know all the other ERCs would probably feel similarly. And at this point, I'd like to turn it over to any questions that you may have. I hope that you were as amused as this baboon is with this magic trick. So I'm going to go ahead and stop sharing, and well, I guess we can go. Jessica can help us with questions.
Yes, thank you so much for this wonderful presentation. The questions are coming in. Again, if anybody has any questions, please enter them into the Q&A box and I will start asking them now in lieu of the chat because I will not look at the chat. So the first question, what current commonly available tool would you recommend for using a quick assessment? Recommend using for a quick assessment to determine if a more in-depth assessment and tool should be completed?
This is incredibly self-interested and biased. I like the fatigue failure tools to duet and lift. Shoulder tools a little clunkier to use, but I'll tell you, lift very quick and duet very quick and easy to do, and they'll give you that quick first survey look. And then the deeper dive, at least at this point, my estimation, involves some professional judgment and possibly a little bit more biomechanical analysis. But I like those tools. They're in the notes and you can check them out. They're on free online with downloadable Excel versions too.
And I did want to also say, yes, I will be sending out a copy of the slides with those links attached to it. So you guys will have access to those links.
I will say this too, when I did my dissertation work, this a while ago now, but at a large automotive manufacturer, 3 tools rose to the top. The Nash-Lifting equation was very good in predicting low back problems. Sue Rogers' model was good, and the strain index seemed to be predictive. And I know there's now a multitask strain, that's a revised strain index that's out. So I'd assume that would work probably fairly well as well. So any other questions?
Also, I see that there's some links in the chat from, I think, Dr. Bandekar.
All right.
Okay, so the next question, also gratitude for the great presentation. Curious about your thoughts on including multiple exposure types within future multitask assessment tools, i.e. mechanical exposure, muscle fatigue, etc. Should tools be restricted to specific tissues and modes of loading, i.e. exposure types? Or do you see a path forward where a tool might aggregate risk across multiple exposure types, multimodal, multitask tool?
Wow, that is the holy grail. Do you want
I can take one. There's a lot packed into that question. I think one area that has a lot of promise for sort of being multimodal is some of the psychosocial stress, because it affects your ability to heal and the propensity for you to get injured in the first place through a number of etiological means. I would say that has a lot of promise. An area that I'm curious about is sort of heart rate variability as a measure for what is that readiness, what is your current healing capability. I think there's a lot in that particular space. I think for a lot of the tools, they are focused on particular tissues because oftentimes, and this is for good reason, people want to have an etiological reason for why somebody gets hurt or injured. And by focusing on a single type of tissue or single joint, it's a little easier to find that smoking gun.
I will say also in my experience that even though a tool says it's designed for a particular area, there is some overlap into other areas. For example, the high scores on strain index, not only distal upper extremity, not only elbow to fingertip, you're probably more likely to have shoulder problems too. We've looked at some of that with the automotive study where we saw relationships there. Similarly, with the Nash-Lifting equation, shoulder injuries are correlated with those, associated with those scores too. So,
which would be another, in addition to sort of psychosocial stress, any previous injury seems to be an indication that you're likely to get injured in another area. So it's just another good predictor. And again, it may be because of guarding, it may be because of general wear and tear and healing response.
AJ, if you're on the call, but AJ did his dissertation work looking at a lot of these factors and looking at the relationship of one injury to another and the odds ratio of developing a subsequent injury when you have an injury to a related body part. Turns out hip, knee type and ankle, foot injuries can contribute to back pain as well, and predictive of it. So yeah, I love the idea of a holistic. Here's AJ. Go ahead, AJ.
Does she have to unmute him?
Oh, he's got.
Yeah, I think it's just now switching over. I went ahead and promoted, so it might take to get unmuted.
All right.
He got promoted.
Congratulations on the promotion, AJ.
There's a new title. Well, we're waiting for him to learn to speak. Is there another question we can answer? Because I know some people are going to have to cut out right at the end. Let's see.
Yes. So let's see. The next question, we have been using RCRA with 3DSSPP and AFF a lot over the past few years, and we love it for all the reasons discussed today. However, the risk indices tend to be very high and they scare our clients. Looking at a timeline for a typical job, relatively little time is spent at workloads less than 5% MVC, which means it's rare to see a job that has sufficient recovery time. Can you comment on appropriate minimum thresholds to count a task in the model?
That sounds like a Murray thing, doesn't it?
Yeah, it does. Or Dr. Potvin.
I'd like to say Carrie is one of the leading practitioners in the multitask models and the RCRA. One of the things that she mentioned about the scary metrics, and one thing that I would say rapidly inflates the metrics is when the force approaches, say if we're setting our threshold for the 25th percentile female strength, which is a sound methodology, but as the force approaches the maximum strength of the 25th percentile female, it's going to say you need a ton of recovery time. It'd be like if you went and did a maximum, just all out maximum bench press. You're going to be, if you did 1 or 2 reps, you're going to need a ton of recovery time. And another problem is your metrics that are anyway, it's a non-feasible calculation, because if you exceed the maximum strength of the 25th female, it's not going to calculate. You're trying to divide something by 0. And so what I found is I've been doing some research with alternative metrics, and one is calculating the percentage of males and females where it balances out, where your calculated recovery time equals your actual recovery time in the cycle where the muscle is inactive. And at that point, we can say, okay, this percent of males and for this percent of females, it balances out and they can perform that task without fatigue. So that's one way that provides a more reasonable metric, although it is a more difficult calculation to make. We're using software, and we have some Excel tools that do that as well. But that's a inherent problem with the RCRA. And also
So can I chime in real quick, Murray?
Yeah.
Because this is an area of a lot of interest to me, and that is personalizing or customizing tools to personal characteristics. And so I think what Murray was kind of going around the edge on a little bit here was that those numbers are scary because they're often based on a very conservative estimate, like a 5th percentile female or 25th percentile female. And so what the absolute truth is, eventually we're going to have to get to what is the risk to the individual worker? If you've got some 6'4" bodybuilding 20-year-old man, he's probably going to be able to lift more boxes to a higher height than a 65-year-old 5'2" woman. It's just, and there are some modifications that we have to look at. So when the numbers come out scary, those numbers are probably scary for that 25th percentile female. And if she's in that workforce doing that exact job, it really is that scary. For your overall population, it may not be that scary. And so over time, I think as we get better with tools, customizing them to the individuals doing the job, we can understand risk much better and protect more workers.
That's a good point, Bob. There's somebody doing the job, potentially even without fatigue. And that's what I found is using that kind of exclusion calculation, set it green for less, if we fatigue less than 25% of the females, and yellow if it's 25 to 75%. If we fatigue more than 75% of them, it could be red. So you can develop your color coded metrics, but that kind of puts it in something that's not, where it's not just through the roof and kind of doesn't make sense.
Right. And it may be through the roof for some of those folks.
Let's see if next
Yeah.
Looks like Ken has a question too.
You want to read it? Looks like
yeah. Ken's got a question. What about accessibility and understandability of the tools to the workers who may have limited formal education, whose jobs or tasks are being assessed? This was in the automotive study that had local ergonomics committees. Almost all the ergonomic assessment was performed by actual frontline workers who built cars when they weren't doing ergonomics, actually. I think you're absolutely correct. That's why I believe that the future requires a deep dive and a quick assessment. The quick assessment should be able to be done by anybody. virtually anybody. For example, the lift tool uses only 3 pieces of information per task: the weight lifted, the distance, horizontal distance in front, and the number of times that it's lifted. Those 3 things come with the damage each task. You do that, it can be done very quickly and easily, and gives a pretty good prediction of overall risk associated with something. One of my PhD students that recently graduated, we looked at incorporating those personal characteristics to improve the model further, but that does the opposite of what Ken, I think, is looking for.
Which is like not adding complexity. I think to Ken's point, that the frontline workers need to understand what the output means, and if they can actually use the tools themselves to do the assessment, that's great. And I think that the fact is that some of these tools can be used, but in any event, we definitely need the people doing the work involved in the assessments of, because we can say, oh, theoretically, this should be really hard. And then we need to know, is the person actually doing it the way that we assessed that they're doing it? And, are they already doing accommodations? And we need to get their input, not just observing them like monkeys in a zoo, but actually asking them real questions and getting their input on how things might be improved. I don't know if that's not actually answering the question, but I think it's just, for all these tools, they really need to be addressing the needs of that worker.
Thanks again. I think if anybody else has any questions, go ahead and get them in the Q&A box now, as we're going to be wrapping up in the next couple minutes. It looks like the last question on here is, are ISO assessment tools used in the United States?
I think they're used to a much lesser degree than perhaps they could or should be. I think, and as a researcher, I'm open to all the different tools that are out there, and to really, I want to see what works, put them in a room, let them fight it out, and let those tools rise to the top. So I don't know. I'm pretty sure NIOSH has recently published a paper on the tools that most commonly used. And I think people go to the same ones that when Murray showed the timeline, we're at 40 years in for some of these tools, and we continue to use them because people are familiar. Maybe they had it when they were in college. I think we need to do a better job as researchers is putting the word out and connecting people to these new tools. We need to start by having a better website, I think, too. It's not as user-friendly as it could be.
Always a good start. Okay, let's see. Okay, just make that big. Okay, here we go. Let's see. So curious how you measure a varied workplace delivery of packages to home environments.
Yeah, this gets back to sampling and what is a reasonable or representative sampling of that job. And we're always going to have that limitation. We did 2 5-year prospective studies when I was at University of Utah, and we had a distribution center that had exactly this problem. How much of the job do you have to look at for it to be representative? And I think that is a great question. A little bit difficult to answer. I think that's one of the problems with some of the single task tools as well, is they conflate repetition and the speed of work and duration of work. And, how do I describe a job that goes really fast, then goes slow, then I pause? What's the speed? If I'm going to pick one speed, it's very difficult to do that. But by being task by task, a multitask tool can capture some of that risk.
I think one answer on that too is taking a statistical approach. Now, again, if you start to try to do binning, you can run into the problems of worst case versus averaging that Murray hit on earlier. But to do a job that's that varied, you have to look at what are some of those worst cases and make the bins as narrow as you can. But you understand that that's going to be a limitation, that you're either going to be under or over representing that risk, or we'll just not have anything delivered anymore. Everybody will work in a factory that is monotask, because then it'll be easy for us to analyze.
Yeah.
Challenge that. The next question is, are there efforts at developing tools that will address extended shifts beyond 8 hours and or low cycle jobs that actually do change from day to day?
Excellent. That's a great question. I'll take that one. Murray and AJ and I have had a lot of discussions about this. We wrote a couple little papers on the concept of an ergonomic control panel. And if you have an ergonomic control panel, all we mean by that is that you've detailed what goes into the job. And so if you're making a model A and a model B of a car, and the Model A does more damage than a Model B, and it's normally 50-50. If you change the make, model, mix, and you knew how much there was damage, for example, from the Model A versus Model B, then you could just automatically update it. The same is true for shift work. If you went from 8 hours to 12 hours, you could increase the load based on what that make, model, mix is in that overtime period. Where it's going to get complicated and we need future research. So if there's anybody out there with mega bucks that just wants to fund it, it's really looking at how do those shifts affect rest and recovery? Because rest and recovery is sort of baked into RCRA and the fatigue failure tools right now, because it's assuming, hey, you've done this work for an 8-hour period of the day, and then we're doing it for 5 days a week. When you multiply by 1.5 for that shift, you've also got another penalty because you're probably losing some rest and recovery in addition to the extra damage. So it's an excellent question. That's sort of the direction that we're moving on. Being able to evaluate that is taking into account what is a true make, model, mix. And that would be a way that you could do it for, like, say, a distribution center where there's packages that are coming of different sizes. You could know what that person's make, model, mix is going to be because you've got that information. Now, you may be knowing what their exposure is after the fact, but knowing it in manufacturing environments, you can often know it a priori, and you can say, oh, wait, this is too much for Jessica. We got to put her, at least some of that time has to be on a different station because it's just too much to go 12 hours at that station. So I don't know if that addresses the question, but it's what I wanted to say.
Well, and we are working on it. I have a PhD student now who just is getting started, works at a local manufacturing company, and we wanted to start to address some of those, looking at how much rest the workers get and try to factor that into some of the models and the quality of that rest. So whether that's by tracking some measure of sleep, in addition to, say, cortisol or other things, these are things we're kind of playing around with right now. And I think that's a great question. And that is one of the directions we're heading. So, all right. Any other questions?
I think that was the last one.
All right. Excellent.
So thank you all for joining us today. For the all of the participants and attendees, thank you for being so participatory and asking all these great questions. And again, for the panelists, thanks for being here and sharing some of this expertise with the team. As a reminder, everybody will get an email tomorrow or in the next maybe day and a half. You're welcome, Dr. Bandekar, and with information about getting your certificate and also the recording and any resources that were mentioned on this webinar. So thank you, everyone, and enjoy your winter season.
Thanks so much.
Thank you.
Thanks.
Well, we got one. Oh, it's a fantastic job. Okay, that's not a question.
There was lots of, it was a fantastic job.